This is a preliminary version of a film now under production at the Stanford Artificial Intelligence Project. This is the Stanford Hand-Eye System. It consists of a mechanical arm designed and built by the project staff and a standard television camera. The arm and camera are both controlled by a PDP-10-6 computer configuration. Luke Ball has been working on the problem of computer control of the arm. We'll first observe some of the capabilities and characteristics of the arm and its world. In order to use the arm, a coordinate system is defined on the table. The arm has 6 degrees of freedom, which allows the hand to be placed anywhere and with any orientation within the limits of joint motion. On the fingers are elementary touch sensors which enable the arm to locate objects by feel. Using these sensors, the arm can easily be centered over an object. The arm's joints are calibrated in terms of angles. This makes possible a solution program which solves for the joint angles necessary to place the hand in any given position with any given orientation. The arm is compliant, allowing it to detect external forces. In order to move an object, the arm control program first computes the set of possible ways in which the fingers may be placed to hold the object. If we wanted to turn the block on its side, the program would then find the range of angle throughout which the hand can reach the object, both in the initial and in the final position. Here we see a graphic view of the initial range. And here we see demonstrated the range in the final position. The initial and final ranges are then superimposed. A solution in their intersection is chosen, as illustrated here by the colored wedge. To simply move an object, the arm should lift it, move it to a location above the final position, and finally place it on the table. When the arm places objects, the vertical direction is no longer free. The arm is moved down at a constant rate until the hand stops moving, indicating that it has reached the tabletop. Of course, there's no need to stop the arm at each intermediate position. A continuous curve may be fit through these points to obtain a smooth motion. The object may also be turned on its side with a twist of the wrist. If we need to turn the object over, then an intermediate position is used to put the object down and to reorient the hand. The arm's capabilities may be combined in the form of a procedure which, given the name of an object and its required final position and orientation, will solve the manipulation task. This is demonstrated as the arm stacks up 3 blocks. If we want to slide a block along the tabletop, one joint is made to comply with the table by exerting a downward force. If the arm had merely been position servoed, any error in the hand's vertical position would have caused trouble. The arm control program can select any number of such free joints and exert a force as it moves. In the case of turning a crank, it is necessary to be able to change the complying joints while the hand is in motion. In this case, the arm has been programmed to locate a bolt by touch and to record where it was. A nut is then centered, picked up, and placed on the bolt. When starting the nut on the bolt, the hand is free in 3 directions and also has a downward force. This ensures that the nut is started properly even if the initial position is not exact. The nut is then turned until the correct torque is reached and the task is completed. Once again, in a close-up view. The arm may be programmed to perform an arbitrarily long sequence of tasks. Alternatively, it may be used interactively with a planning program in order to make future actions contingent upon the current state of the world. Future work planned for the system includes multiple arms and special purpose hands involved in complex assembly tasks. Aaron Gill has been using both the hand and eye to investigate tasks involving precise manipulation and self-correction based on visual feedback. The eye is an ordinary television camera whose picture is digitized into a 256 by 333 point array with 4 bits per point. Thus, a magnified view of the bottom corner of the block shown here would appear to the computer as an array of intensity values like this, where the relative brightnesses are indicated by values from 0 to 15. The positions of the movable joints on both the hand and eye are digitized. These 2 independent coordinate systems have to be correlated to provide a common basis of information transfer between the camera program and hand program. This is accomplished by relating all sensory information to an intermediate 3D frame of reference called the table coordinates. A special calibration program accomplishes this by moving the hand to various positions on the table and then locating it with the camera, as we see here. Once the hand mark has been found, the difference between this location and the predicted location is measured. This difference, called the image error, is then used to further correct the hand-eye coordination. To recognize the hand, use is made of the black rectangles called hand marks painted on the fingers. The corner finder program is used to find the lower corners of the hand mark. To economize on scene analysis time, the corner finder only analyzes a small rectangular region of the scene. We see this region indicated on the camera's monitor screen by a blinking white rectangle called the cursor. The cursor is first positioned at the predicted location of the lower right corner of the hand mark. The operation of the corner finder is shown in this display. The corners and edges are found by fitting line segments to the boundaries between light and dark regions. If a suitable match to the expected result is found, the program looks for the lower left corner using the position indicated by the current location of the right corner. The technique of visual feedback has been used successfully in several manipulation tasks, such as precise stacking of cubes, shown in this slow motion sequence. The program must first determine the image error at points near each block. A hand is positioned over each and a hand mark is located. The image errors are recorded for both positions. The hand is lowered over the top cube and the fingers slowly closed until a touch sensor makes contact. By using the known dimensions of the cube and the fingers, the vertical plane of the hand mark is found. Locating the hand mark with the camera gives us a known line along which the mark lies. This, along with the vertical plane, is sufficient to locate the hand in space. If the hand is not yet centered directly over the cube, it is repositioned, and the process repeats until the error tolerance is met. Any remaining error is noted. Finally, the cube is grasped firmly between the fingers. Next, the camera is centered on the base cube. We then begin looking for its top edges. First, the left edge is located, and then the right. From this, the position of the upper middle corner is computed. The top cube is then lowered until it meets the resistance of the bottom cube. Thus, the vertical position of the top cube is exact. The hand mark is located to update the image error for the new hand position. The program uses the corrected hand position information, any grasping error noted when picking up the top cube, and the known size of the cube to predict the image location of the bottom edges of the top cube. This prediction is then used to search for these edges. Here we see the discrepancy in the left edges clearly outlined on the intensity map. And here the edges on the right side are checked. The intersection of the bottom edge line, along with the known height of the second block, serves to locate precisely the lower corner of the top cube. Horizontal position error is then computed. The top cube is now lifted and repositioned. This process is repeated until the error is within acceptable limits, generally requiring no more than 2 iterations. Here we see the final precise alignment of the cubes as shown in the analysis of the intensity map. A simple extension of these techniques makes possible many complex manipulation tasks. As one example, we see here the system working a child's toy, which requires it to insert each of 3 different objects into its correct hole. The holes are only 1/10 of an inch larger than the objects. These techniques should prove very useful in the future for complex assembly and construction tasks. A recent addition to the hand-eye system is the new laser ranging device implemented by Jerry Agan. The essential parts of the system are a laser, seen under the table, a deflection assembly containing a cylindrical lens and a rotating mirror, and the television camera for detecting the image. On the left, we can see the deflection assembly. Visible in the foreground is the periscope, which brings the light up to the level of the table. A plane mirror sends the narrow beam into the deflection assembly, where it is broadened by a cylindrical lens into a plane approximately 2 millimeters thick. This rotating mirror then sends the plane to the selected locations in the scene. The plane's orientation may be controlled by the cylindrical lens as well. plane intersects objects in the scene to produce a line which follows the surface of the object. We control very precisely the position of the mirror and the cylindrical lens, and hence the orientation of the plane of light. Here the doll is scanned once again with the lights out. A television camera analyzes the scene for the presence of this bright laser line. Using the orientation of the plane of light and the location in the camera's image of the bright line, we can compute the three-dimensional location of points along the line. The data obtained in this manner are pre-processed for noise rejection, smoothing, and data compression. Each line segment found is fit with one or more straight lines or ellipses. Here we see the result of sweeping the plane across the scene horizontally and vertically. The visible surfaces of this S-shaped tubing are clearly outlined by the cross-hatching which is produced. Here is the result of the same process using the more complex shape of another doll. Each of the fitted segments is interpreted as a line in three dimensions. Here we see the fitted surface of the tubing. The projections of these lines may be computed for a hypothetical observer located at any position relative to the object. Continuously varying the observer's angle gives an illusion of depth, demonstrated in the three-dimensional nature of the computer's image. Here is the result of the same process applied to the surface of a baby doll. We would like to be able to describe these figures in a simpler, more informative representation. For this purpose, flexible cylinders or cones, called generalized cylinders, are used. A generalized cylinder consists of an axis, a curve in free space, and cross-section descriptions along this axis. As the first step in fitting these generalized cylinders, a preliminary analysis program locates in the image laser traces which are close to one another and parallel. Here the process begins with a section of tubing. Such traces indicate that the object has a reasonably smooth surface of fairly constant radius at this point. The center points of each group of curved segments is used as initial assumptions for the cylinder tracer. The tracer then determines the diameter of a cylinder and fits circles to the cross section. As the baby doll figure is processed, you see the program performing the important task of segmentation, isolating each generalized cylinder from the rest of the object. Major changes in cross-sectional diameter are used to determine cylinder endpoints. The doll may be described by 6 cylinders, one each for the body and head, 2 for the arms, and 2 for the legs. present, the program assumes only circular cross-sections, but work is underway to deal with a more general description. In addition, efforts are being made to enable the program to link together cylinders into a skeleton which represents the figure. Object recognition routines operating on the representation will then be able to classify.